So this talk comes from conversations over the years with developers about security. And one of the things that I've wanted to do was to just remind people about the value they get out of the JVM. And so this talk is a whirlwind take through what the JVM does for you that you may not be aware of. And in some ways, that's okay not to be aware of it, but it's nice occasionally to be reminded that these things exist. So we've talked about me. Let's move on. Before I start talking about the tech stuff, the important bit is that you understand why this is important. Security is always important, but security nowadays is vitally important because the scale of the challenge. So if you were to look at the illicit drug trade, then that makes about $450 billion a year for the bad guys. So $450 billion, massive amount of money, but it pales when you look at cybercrime. So the numbers for assessing how much the bad guys make with doing this is challenging, of course, because you can't ask them how much money do you make. You have to look at it and you have to make some assessments. And what they do, and these numbers are things that you can go find on the web. These are government organizations working these numbers out. And currently, the estimation for this year, it's about $9 trillion. So $9 trillion is just an unimaginable amount of money. But as you can imagine, it's significantly more than $450 billion, and it continues to rise. So there is an enormous amount of vested interest in many people around the planet in using cybercrime as a way to make money, steal data, all those sorts of things. So you have to understand that security at all levels is a vital problem that you need to be part of, and you need to understand where your defenses are. Hence a little bit about this talk. Because as we're beginning to realize is that this guy, if he was still around, would not have probably picked the drug trade as a way to make money, because smart guy would probably have picked a laptop instead and been joined the big army of cyber criminals. So let's look at this from a technical point of view. You've got to understand that the way that security works, the way that attacks work, have changed. So I will use the term exploit first, and it's something that you should be aware of. As a developer, you probably don't get much involved in the cybersecurity side of JVMs and things like that, but there are things for you to do, and I'll talk about those later. What you have to understand is that the way that attacks take place, often they are attacks making use of vulnerabilities that have only just been reported, or quite often haven't been reported yet. So there are many occasions where issues are found, bad guys exploit them, and eventually they get reported, and then eventually somebody says to you, you can update a dependency because there's now a fix for it. So you have to understand, because you have all these bad guys on one side who really want to get into your systems, that pressure and that interest and that sheer amount of resources to do this means the way that security works for us is different than it used to be. So you have to be aware that if any exploit is found, if you have any vulnerability in your system, you're on the clock, and the clock is very short to get fixed. So having said that, now let's look at the attack vectors. So how do bad guys get in? So let's talk about a JVM first. Well, I'm going to go through this in more detail, but if you were to draw classic pictures of a JVM, you would have a picture sort of like this. There's a layer at the bottom, which is where the operating system is. There's the yellow boxes at the top. The smaller one is your code. The bigger one is all the dependencies that you use, because modern applications, obviously, we all rely on enormous amounts of other people's open source projects to give us the value. And in between is these layers of stuff, JITs and class loaders and interactivity with native systems. You may have heard about JNI. You may know about system classes. Maybe you don't. But there are bits and pieces. The first attack is way at the bottom. The first attack is the environment. So the first attack is getting into the files that your JVM relies on, your JDK relies on. So config files, execution environment, anything that your application or the JVM relies on, if it sits on the disk, if it's on the file system, and that includes the scripts that are used to launch your things, they are vulnerable. Unfortunately, those vulnerabilities are your problem. It's not something the JVM can do. The JVM can be careful about validation, but ultimately keeping the JVM environment safe, the place that you run it, the scripts that you launch, that's your problem. And one of the things, the reason for saying this is I want to point out something because we have this conversation a lot. There's a sense that developers think that if people can get access to a system, then they're able to change a file, they can change anything, and therefore the whole system is compromised. And that's not true. There are many, many instances of vulnerabilities that let, almost like a letterbox, a peephole access. The bad guys can get to something. And sometimes that can just be one file, sometimes it can be bigger. But you have to understand that it's not just about, it's not a thing you should not worry about, because the idea that if people can access your systems, then they can do anything is not true. Imagine that they can get in through the letterbox in your house and they can get just so far. They don't have full access to the contents of your house, but whatever they can reach through that letterbox. And that's a real physical thing too. So there are things that they can pick up, there are things they can attack, and of course, these scripts often, some of these things sit up on open source, and in open source they could be compromised. So you have to worry about how you launch an environment and what the configuration file looks like and all those things. But that's your problem. That's not a JVM problem. So I need to call that out because you need to appreciate where the lines are. Right. So what can the bad guys do beyond this? Well, there are various ways, and I'm just going to touch a few of them in the timescale. So can they change the bytecode? Obviously, we load Java code. It's bytecode. Can they manipulate that? What about the heap? All our objects created in Java in heap, can they corrupt that? Is that possible? And what about loaded code? Can they bring code in from somewhere else? And all of these are things you might consider to be possible. And so we're going to go through these and look at what's actually possible and reasonable versus what's difficult. So to do that, we have to talk about what a JVM really is. And so I had one picture for you of what a JVM is. Let's look at a different picture. Look at this picture, and big word in the middle, virtualization, because it's a Java virtual machine. And the virtualization is building this layer and bringing all these different parts in. So there's a big part of this is dealing with the operating system, the hardware, the file systems, the UI. Lots and lots of these different combinations are what make up a particular platform, the threading model, the architecture, the hardware, those things. And that is what a JVM is. Well, it sort of is. That may be what you think it is. Maybe you haven't appreciated just how complicated these things are. There's a lot of work here. So what the JVM is a structured abstraction. So it looks at all those different pieces and draws boxes. And so you'll be aware of the just-in-time compiler. You'll be aware maybe of native code. You may have used JNI. You may be aware of class loaders. It's something that we all use, but maybe it's not obviously in your radar. And class loaders are things that allow you to load local code and remote code. And then there's a structure, there's a layer in this abstraction that talks about the operating system and the UI and all those sorts of things. So it's a structured abstraction. But that picture you're looking at isn't really what it is. What a JVM isn't really that picture. A JVM is simpler. So a JVM has a specification for the memory. It has a specification for the CPU. It has a specification for the threading. It has a conversation about native code and jitting. You can see, these are the simplified models. Yeah. Actually, this is too complicated. This isn't even what a JVM is. A JVM is actually really, really simple. So a JVM has a small concept of locks. It understands about locks. It has no understanding about threads. It understands about object references, but it has no understanding about memory. Objects and classes and things it knows about, but where they're stored, how they're accessed, that's not part of the specification. It has a sense of what a JVM, what a CPU looks like, but it's not the CPU that you would normally use. To bring all the different items of the CPU together, the JVM uses a very, very simple stack-based model. And that stack-based model, as far as I'm aware, there's no particular hardware out there that matches that. It is certainly you get software versions of these sorts of models, but from the spec point of view, the JVM says, I know about objects, I know a little bit about looking, because I want to be able to synchronize access to objects. I know about CPUs because I've got a stack-based CPU. And that link that you see, you can go off on that and you can see all the details. That's the JVM spec, and all the JVMs that you've used honor that spec. So that gives us some magic to do. So the defenses we get against the bad guys come from these characteristics. So the first one is it's a one register stack. So that means that the only regular you can't manipulate this register. So it's a program counter. If you've tried ever to write assembler, you know about registers, but there's also a thing about a program counter where it says, which is my next extraction to execute. There's no way within the JVM to access memory. Right? There are no pointers. Pointers don't exist. It's literally aware of objects, and that's it. It's no way you can't go from this architecture. You can't reach the host environment. There's no threading. As I said, it's just basically what's there to prevent one potential of thread, but it doesn't know what a thread is from accessing objects. And there's no way of getting the CPU, right? It is really, really simple. And there's no way of breaking out of this. And those unspecified features, so the memory management and threading and JITs and things like that, they're not in the spec. They're just relied on. There is this understanding that these things are necessary. So garbage collection moves stuff around in the heap, and therefore, and it's always doing that. And so it's very hard for a bad guy to figure out where something is because it moves. It's not like static memory layouts where it can work out maybe where you stored a password. It's got to figure out which object it is to find that. And finding objects is really hard. How do you find an object inside a heap when you have no specification for the memory layout? And ditto with threading. There is a little tiny leaky thing at the moment called thread affinity, and that's about to go away. But the ability at the moment to take a Java thread and break out, reach the native stuff, and maybe reach native operating system structures and things like that, you can't do it. There's no connection between the Java and the base and the physical stuff. I say there was a little bit of it, but even that wasn't particularly a dangerous thing, and that's going to go away. And the JIT gives us an enormous amount of security. So there's lots of things going on with JITs. It depends which platform you've got, but there's lots of things like it's compiling code and it recompiles, it optimizes. So the bytecode that your application has created, or rather what your application is, that gets converted into machine code by the JIT. and then it gets turned done differently, and nobody can predict really what your machine code is going to look like at any one instance for your application, and it's not configurable. There's no way for the bad guys who've got some Java code to get to the JIT because the JIT doesn't exist as far as the JVM is concerned. So there's lots of the benefits we get are from these unspecified features. The bytecode itself is also really simple because it's a stack rate based process. It's designed to represent the least complicated CPU that we could think of, virtual CPU. It's got a whole bunch of designs so it can be verified because we don't want to crash the JVM because we've got bad bytecode. The JIT does verification as well. It's really hard. It's impossible, really, to construct bytecode that allows you to break out to the operating system because there is no assembler instruction that lets you get to real things. All you can do is manipulate what the JVM does for you. And as I said, the JVM is really simple. There's no way of forging a pointer because pointers don't exist. And if you want to go from one object to another, then you use the bytecode as designed. But you can't say, let's wander around the heap, because that's not an instruction that's possible. There are things like class loaders. Now, we all use class loaders, though we may not realize it. The class loaders are supposed to separate code so that you can prevent less trusted code accessing more trusted code. We tend not to do that. We tend to use these things fairly straightforwardly. So what you do tend to see is people, you've got Bootstrap class path, you've got the extensions class path, you've got the normal one, and quite often all the bad guys will do will see whether they can target that environment and change your class path. Right, I need to move on a little bit. So the final thing was remote code loading. The JVM sort of was built on the idea that you can load remote code. It's not a good idea, but it's there. And this little diagram represents log4j, which I'm sure we're all still dealing with. And log4j made use of not JVM capabilities, but the next layer up and made use of JNDI, etc., to load bad code. And unfortunately, the big weakness that we have in the Java, which is again something which is more down to you to fix, is serialization. So the loading of remote code is still a serialization thing. Serialization is used everywhere. I mean, please don't think it's gone away. It's in absolutely everything. And anywhere you can find object input stream. So I went to Google, to GitHub, and said, how many of these can I find that's in Java? There's loads of these. Object input stream is the key piece of serialization for bringing stuff in. Serialization is so performant that there's no real other alternative, though there are things out there that people can make use of that would give them the same performance, but we're sort of all embedded in using serialization. On GitHub again, I said how many classes have implement serializable? 15 million hits. Right. So the JVM does have defenses. So serialization is a big topic. So I really can't go into too much detail. But JVMs have things called class filtering, where you can specify in a config file some rules about what you're allowed to be instantiated, how big arrays can be, and things like that. It's there. It's not the perfect defense, but it certainly is something you should be looking at. The other parts of this are modularity. If you've probably not used modularity, because modularity is something that we've all sort of ignored, but you should all be aware that modularity is core to how the OpenJDK design team think, and that everything comes around modularity. So if you're not using modularity, you might want to take another look. Modules give you things like JLink, where you can throw away large chunks of the JDK that you don't need and create your own custom runtime. Less code, less attack vectors. Um, Downside is you have to recompile the thing yourself. If you still don't want to use modules, then you should start looking at sealing the jar. Jar sealing allows you to control where code in particular packages gets loaded from. So it means that you can spot if classes in a particular package are being loaded from two different jar files. And if you do this right, then people can't subvert your code or your dependencies because sealed jars prevent that cross jar loading, and you basically get an exception. If you still want to use serialization, which obviously we still do, then start thinking about whether you need to share the objects that are part of your application design and whether you start thinking about using less sensitive objects. And one of the obvious ones is to look at records. Records are really great. Records are very easy to create. I mean, they're just very simple. And because they have no um, code associated with them, they're just data, it's harder for the bad guys to use it as a way to trigger running bad code, because serialization attacks is all about how do I get your Java application to run in ways that you weren't expecting. Right, so the last one in here is vulnerabilities. So I started with this talk talking about $9 trillion and how bad that is. A large amount of the attacks that we are all under comes from vulnerabilities. And the vulnerabilities come from the dependencies that we consume. And we all rely on this code. So we have nowadays, the amount of time you have between a vulnerability, serious vulnerability being reported, and the time between that and you updating is minute. It's in some cases it's less than a day, sometimes it's even less than that. If you were to keep your dependencies up to date, you would avoid all of the large amounts of attacks that come down this way, right? And you'd get some other performance as well. The horrible thing we noticed is that pretty much as Java developers, when we download something, we go to Stack Overflow or ChatGPT or whatever, and we get some coordinates, and we stick it in the dependency in the POM or the Gradle thing on. We don't check to see if there are better versions. And so often, if you were to just check to find a better version, you would avoid all the risk that you have at the moment. So as you can see, 96% of vulnerable downloads. For everyone that you so often from Maven Central, we see that if you download something, there's a better version that you could have downloaded, a less risky version. So by fixing this problem, you would make the world a lot safer for your application. And actually, it would save you a whole bunch of time because by continually having to patch when you have in this mode, you're always in panic mode. So having a process where you can keep your vulnerabilities updated on a regular basis and you've automated that means you've got a slicker process, which tends to mean that you're more productive. So there we go. Wrap up. The JVM design has just really good at keeping you safe from different types of attack. It's there, it does its job, it keeps you safe. It's still your job to keep the environment safe because we can't protect you outside that. Serialization is still a major challenge, and you need to do something about that. You need to think about how you're using it and whether you can use alternatives, things like Xstream and things like that. There are better alternatives. And number one is spend some more time keeping your dependencies up to date because that will pay off much more than probably anything else. And there we go.